Hello and welcome back to EGR 151 Electrical Machinery. In this third unit in our section on inductors, we're going to be looking at resistive inductive or RL parallel circuits. So we've looked at circuits with just inductors, and then we looked at circuits with resistors and inductors in series, and we're going to wrap up this conversation with resistors and inductors in parallel. So once we've completed this unit, you should be able to talk about the operation of a parallel circuit that has both a resistor and an inductor in it. You should be able to calculate the various circuit values for our RL parallel circuits, and you should be able to put together an RL circuit, at least know how to, and measure the circuit values with test instruments. Again, know how to do that as well. So to give you an idea of what we're going to be covering, we're going to be looking at essentially a very similar circuit to what we've looked at before, but in this case, we're going to be looking at situations where our resistance and inductance elements are in parallel, so inductors and resistors in parallel. In terms of our mathematical calculations, they're going to be used to determine a number of different electrical quantities. We want to know what the current and voltage is for the entire circuit, but unlike all of the circuits we've seen so far, this one is going to have multiple branches. As a result, we now need to know what the current is going to be through the different branches, through, for example, the resistance branch and the inductance branch. So here's our example, right? We have a AC power supply, we have a resistor, and we have an inductor. And clearly, since they're going between the same nodes, the resistor and inductor are in parallel. Now, our AC power supply is going to put out a voltage, and because they're going to be in parallel, the voltage across both the resistor and the inductor are going to be the same. So the voltage must be in phase, right? Because it's the same voltage, right? There's no way that it can be different between these two. So what else is going to change? So it turns out that what actually changes is the current. If we look at our resistor, we have the voltage, right? This is the voltage across both branches. It's our output voltage. And we know the current is going to be in phase with the resistor. It's just going to be scaled by the resistance. On the other hand, when we look at the inductor, our voltage again has to be the same on both branches, but we'll notice the current in this case is going to lag the voltage. So it's going to be behind the voltage. It's going to be behind the voltage by 90 degrees. In terms of representing this vectorially, our current in the resistive portion of the resistive branch is still going to be represented along the x-axis, but because the inductive current is out of phase by a positive 90 degrees, it's going to be shown below or along the negative y-axis. Now, in terms of the overall analysis, it doesn't make a huge amount of difference, but this is the standard representation in terms of the way parallel circuits are represented vectorially. So let's look at a simple example. Here we have a 240 volt AC power supply that's powering our parallel circuit with a resistor with a resistance of 15 ohms and an inductor with an inductive reactance of 20 ohms. What we want to find is values for the total circuit, for example, the total current, impedance, our apparent power, power factor, and our phase angle. And then we want to find our electrical quantities for our various components. For example, the voltage across the resistor, current across the resistor, power. For an inductor, voltage across the inductor, our current through the inductor, our reactive power, and our inductance, right? So calculations for the resistive branch is pretty straightforward. We know our voltage is 240 volts. We just use Ohm's law with our 15 ohm resistance, and that gives us a current flow of 16 amps. In terms of our power, a number of different power equations we could use, but now that we know our current and our voltage, just multiply those two together, 240 volts times 16 amps, and that gives us 3,840 watts. I could also write it as 3.84 kilowatts if you wanted to save a little bit of space. In terms of the inductive branch, well, we still have the same voltage, right? The voltage has to remain the same. It's between the same two nodes, so it's 240 volts. And then we have our inductive reactance of 20 ohms. That's going to give us a current through the inductor of 12 amps. In terms of our power-like quantity, right, our reactive power, it's going to be, again, the current, I should say the current times the voltage, 240 volts times 12 amps, and that's going to give us 2,880, in this case, volt amps reactive. Right, so that's our apparent power in units somewhat similar to watts. Lastly, we can calculate our inductance. We know our inductive reactance, that's that 20 ohms. We have 2 phi and a frequency. The fact is, for most of our power supplies, the frequency is going to be 60 hertz. So if you take 60 times 2 pi, you're going to get 377, right? And we take 20 ohms divided by 377, we'll get an inductance of 0.0531 henries. You could also write this as 53.1 millihenries. Again, those prefixes are ways to oftentimes save a little bit of time and energy and make the answer a little bit more clear. So in terms of our total current for our circuit, well, keep in mind we have the current flowing through the resistive branch and we have the current flowing through the inductive branch, but since they're out of phase with each other, we need to add them up vectorially. And in terms of this, we have our two values. We can show you mathematically how we go about creating those, but of course we'd use one acting to the right, one acting down, and then the resultant would be our total current starting from the tail of the first one to the tip of the last one. Here's our calculation. We're just going to use Pythagorean theorem. We have our current flow, that was 16 amps through a resistor. We have our current flow through the inductor, that was 12 amps. Because we have to do this vectorially, we're going to square both of these, add them up, and take the square root. And it turns out that our total current flow is actually equal to 20 amps. Now, if you're going back and looking at the relationship, again, 12, 16, and 20 turn out to be, again, a 3, 4, 5 triangle, in this case, just ramped up by a factor of 4. So here's how we could plot this out if we want to use the parallelogram method, right? We have our current going to the right in our resistor, our inductor going down, and if we want to close off the parallelogram, that would be our total current as well. Now, in terms of our impedance, right, that's our Z, that's going to be based on the total voltage and the total current. The voltage in this case here is 240 volts. Really don't have to label it as total because the voltage is the same throughout. We just calculated what our current flow was, which was 20 amps, and it turns out that Z is going to be equal to 12 ohms, right? We could also do this vectorially by adding up the resistance and adding up the reactance, but we would have to use the reciprocal method. Remember that, how we would do this with parallel? So 1 over Z would be equal to 1 over R plus 1 over X sub L. You'll still get 12 ohms, but this is a little faster way to do it if you have this information. Now, in terms of our apparent power in volt amperes, we could just use our total voltage and multiply it by our total current. Our total voltage is 240 volts, our current 20 amps. Multiply those together and you get 4,800, and this would be in those volt amperes. By the way, we could do the same thing if we determine the power from our resistor in watts, power from our inductor in VARs. This would be, of course, the reactive power, and we can combine them vectorially to solve for our apparent power. We get the exact same value. one thing that you may notice is you'll notice that these are not in the same direction as the current flow. It turns out that when we're dealing with power, they're always considered positive. So power always adds up. Now, in terms of our power factor, again, power factor is that ratio between the portion of the power being used by the resistor versus the total apparent power. We can do it a few different ways. For example, we could just use the current, because that's the same ratio. We could use the impedance, right? And the resistance, or for that matter, we could use the power, right? This is the power from our resistor, 3,840 watts. This is the total power, 4,800 volt amperes. Divide those two, you get 0.80. It can also be represented as a percentage. If you want to multiply it by 100, you'll get 80%. Another important circuit value that we need to calculate for is the phase angle theta, right? And in terms of that, we could use our power factor, right? Remember, our power factor is 0.80. That's going to be equal to cosine of that angle. If you determine the arc cosine of 0.08, you'll get 36.87 degrees. By the way, you can also do it using the power values. You could use the current values. So a number of different values could be used to determine this relationship, and they'll all turn out to be right around, they'll be the exact same value, right around 37 degrees. So what does that mean? Well, if you recall, our voltage shown right here, it's the same voltage everywhere because it goes between the same two nodes, but the current is going to be off by these 37 degrees or so, 36.87 degrees. And what I mean by the current, that's the total current for the circuit, right? Because it turns out the portion of that current is going to go through our resistor, a portion of that current is going to go through our inductor. When those two are combined, it turns out that our current is going to be 36.87 degrees out of phase with our voltage. So finish this all up. Let's fill in all our values. We had started with the 240, 15 ohms, and 20 ohms. Through our calculations, we were able to calculate all of these various values in terms of this. So we have 20 amp of total current. We have a impedance of 12 ohms. We have an apparent power of 4,800 volt amperes. We have a power factor of 0.8 or 80%. Our phase angle theta is equal to 36.87 degrees. In terms of our resistor, it still is 240 volts. By the way, they're all 240 volts because they're in parallel. In terms of our current flow, 16 amps, 12 amps. Notice these two don't add up. They got to be added up factorially. And in terms of our power, 3,840 watts. That's the true power in our resistor. And our reactive power in VARs is 2,880. Again, these are combined vectorial for an apparent power of 4,800. And lastly, this is our inductance for this particular inductor, 0.05331 henries or 53.1 millihenries. So to summarize what we covered in this unit, it turns out that our voltage is going to be the same throughout all of our various components because in this case it's between the same two nodes. So units, components in parallel always have the same voltage. In terms of the current, we have two branches, and in the current flowing through the resistive portion of the circuit is going to be in phase with the voltage, so lined up. On the other hand, the current flowing through the inductive portion of the circuit is going to lag the voltage, in this case by 90 degrees. In terms of the total current, you need to add those two up, right? And it's definitely going to be the sum of the individual currents, but keep in mind, because they're not in phase, they need to be added up vectorially, right? And to do that, we can use a number of different techniques, but primarily we're going to use Pythagorean theorem. In terms of the overall impedance of our RL circuit, we can do it a couple different ways. We did it in our example where we used the total voltage and total current flow to solve for our impedance, but we can also do it by summing up the reciprocals of the resistance and the inductive reactance, right? So 1 over Z is going to be equal to 1 over R plus 1 over X sub L. In terms of our power, we have true power from our resistor. We have reactive power from our inductor. We need to combine them to determine the apparent power. Again, they're out of phase, so they need to be set 90 degrees from each other, and vector addition needs to be used to determine the amount. One thing to point out that in each of these cases, the same phase angle is used for power, for current flow, etc. So as always, there's additional resources in your textbook and online. And of course, if you ever have any questions, do not hesitate to get in touch with me.